Hello, everybody. How's y'all doing? So, I know it might seem also, goddamn, this light is looking like fucking God's gonna show up in my room any second now. Anyway, I know I haven't uploaded in a while, even though I did say that I probably would, but again, I said probably, so. I know one person who's gonna be happy to see this. Shout out to you, you know who you are. So, enjoy, I guess. But yeah, recently I've gotten into math, right? I switched majors from engineering to math. So here we are, and I actually got interested in math. I've picked up a couple new hobbies recently, got into investing and studying just in general, some music stuff. So it's pretty sick, I'd say. But I was watching some math videos today, just for fun, and something came into my mind basically, right? And I was like, all basically like since school, right? We've been taught about math and radicals and fractions and numbers, in general. But for some reason, this always struck me as weird. The first, or one of the first irrational numbers we ever were introduced to was pi, which is used for geometry purposes for, circles and stuff, area circumferences and stuff, and then you see it in calculus some more. And then there was the radical 2, which is another irrational number. Now, I didn't really understand why radical 2 is special, because radical 2, first off, let me start recording on my tablet, and I'll be back. Radical 2, right? Like radical 3, radical 5, radical 7, and many others like them, basically, are irrational numbers, which means you can't write them as, like, this isn't equivalent to some fraction, some x over y. There's no x over y that'll give you exactly radical 2. You can get really close to radical 2, like to certain at a certain accuracy by doing, if I'm not mistaken, 99 over 70. Let me just fact check this real quick. I think it should be 99 over 70. Yeah, 99 over 70. You get decently close, like, actually radical 2 is 1.414287, and 99 over 70, I'm actually just going to do this right on my calculator, right over here, so I can show you what it gives me. 99 divided by 70 gives you, oh, this is flipped, 1.41428, whatever, right? Actually, wait, this is, yeah, it's pretty accurate, I'd say, right? 99 over 70 to radical 2. But the thing is, why is radical 2 kind of like thought of more? Like when you talk about irrational numbers, even like when you see them in YouTube videos, something as trivial as that, they always show radical 2 instead of something like radical 3, radical 5, even though any radical x where x is a prime is irrational, because prime means that you can't write it as like it doesn't have factors multiplying. Like for example, 9 can be written as 3 times 3 and 9 times 1. 2 only has 1 times 2. That's why it's a prime number. So any prime number written under a radical would be irrational. The answer to it would be irrational, right? So why is radical 2 so important? Well, it kind of is, but also not as important as you might think. The thing is, it's really the first one you think of, right? It's like, oh, okay, 1 plus 1, 2, oh, radical 2, like, oh, what's that like, Another reason why it was actually thought of first was geometry. So if you have a very basic triangle with an equilateral, an isosceles triangle, I guess, with sides 1 and 1, so finding this length, people might have thought about, like, oh, they learned about the Pythagorean theorem, right? Which says that a squared plus b squared equal to c squared. And now knowing a, let's say this is a, and this is b, right? Knowing that each of these is 1, so you get 1 plus 1 equal to c squared, right? So you're saying c squared is equal to 2, so c is equal to plus or minus radical 2, but negative radical 2 as a side doesn't make sense, so c is equal to radical 2, right? And then people were like, so, okay, how long is this actually? Like, they were probably cutting wood or stone or something. They were like, okay, radical 2, what is that? Like, how much is that? Like, a radical 4, right? If this was like a 2 plus a 2 here, then you'd get a 4. Okay, a 4 centimeters or 4 inches, 4 meters, it makes sense. Radical 2 doesn't. I think that's where it came from, like as a first sort of thing. So yeah. Interestingly enough, radical 2 is also used in sort of, how can I put this? Like, formulas and equations and stuff. So there's something called the Silver ratio, which has radical 2 as part of it. The Silver ratio, I haven't even looked at this, I'm just looking at this right now for the first time. The algebraic form of a Silver ratio, so Silver ratio, right? It's 1 plus radical 2, right? And what the Silver ratio does, apparently, is the ratio of the larger of those quantities to the smaller quantity is the same as the ratio of the sum of the smaller quantity plus twice the large quantity to the large quantity. What the fuck is this? Same as an allusion to the... Okay, anyway. Apparently, Silver ratio is a thing that people do and need for some things. So there's also something called the Gelford, what is it? Gelford-Schneider constant. Schneider constant. Also, yes, my handwriting is as. Thank you for noticing. Which uses the radical 2 in this way. It says 2 radical 2, and yeah. And what does it use it for? So, which was provided to be a transcendental number by Rodium Kuzmin in the 1920s. In 1934, Alexander Gelford and Theodor Schneider independently proved the more general Gelford-Schneider theorem, which solved part of Hilbert's seventh problem, described below. Square root of the Gelford. Okay, so apparently it's a transcendental number. This is ending up to be a fucking Wikipedia deep dive as to why this is all important in math. So, yeah. So this is the square root of 3 that I'm looking at right now. Geometrically, it also has a representation, and the representation is this. So it's the height of an equilateral triangle, the sides of 2. Yeah. So radical 3 would be... This is a horrible equilateral triangle. Up. Yeah, there you go. I'm butchering this. Anyway, so if all of these sides are 2, then radical 3 would be this. Which makes sense, because height, and you'd have... How much? Yeah, you'd have... I mean, this is 2, this is 1, so by Pythagorean theorem again, you get 1 plus... It would be 4. It's equal to c squared, so... C be equal to this, is a heck? If this was radical 2, this would make sense. If this is like... Anyway. Yes, math. So, yeah, I just thought about this for a while. I didn't really come up with any reason to make a video. I was just like, I'm worried, let me make a video about why radical 2 is such a weird, overused, irrational thing. Thing is, it's really not that important. At least that's what I understood from this. Like, sure, it's used in some ratios and constants and stuff. I mean, it has pretty deep history, apparently, even back to ancient Roman architecture. So it is important. I can't say it's not, but really, there's no like radical 2, radical 3, radical 5, and so on and so forth. These are all irrational numbers. I mean, as long as you have a prime number here, it's irrational, right? So, yeah. Now, how... This is a good question. How do you find radical 2, right? So we said, I did say previously that radical 2 is equal to 99 over 70, right? First of all, how do we even get 99 over 70? Why is it 99 over 70? Like, where did this even come from? And second of all, 99 over 70 is only accurate to so many decimal places. So let's say radical 2, I take the first 50 decimal places of it, then 99 over 70, I don't know exactly, but I'm assuming it's going to be something like, okay, maybe 30, or probably not actually. It's going to be probably like what it said in the beginning, around, I think, 13. Right? So that's why if somebody asks me, for example, okay, Antoine, I need you to... Why is this not moving? Damn it. Yeah, okay. Okay, so if somebody asks me, okay, look, Antoine, I want you to find radical 2 to 10 to the power of minus 30 decimal places. First off, I'm going to be like, why? You can Google this, for sure, but it would be interesting to know how to do it. Same as pi, actually. I'm actually now wondering, how do you find pi to 10 to power minus 30? Power minus 30 is a lot. The thing is, if you get the general idea of how to do it, it doesn't really matter. Minus 30, minus 2, minus 3, minus 75. It doesn't matter. As long as you get the main concept of how to find the accuracy of each, you can just keep expanding it. You know, like you can get more and more and more accurate. It's like, I'm taking numerical analysis right now. It's pretty much the same thing, actually. Just trying to mitigate... Well, actually, not mitigate. Yeah, I mean, I guess so. You're trying to mitigate error, like make it whatever. This is a whole different video. What the fuck am I on about? Anyway, so, right. Let me have a look. Okay, first off, I was wrong. Apparently 99 over 70 is accurate to 10 power minus 4. Not bad, I'd say. It's not really bad. So, A. Good enough, I'd say. But let's see. The next two better rationals, actually, interestingly enough, the next better one, so 99 over 70, pretty good. It shows... God damn it. Okay. So 99 over 70, we said, is accurate to approximately 10 minus 4. Not approximately, it is. 10 power minus 4. Accuracy. Weirdly enough, 100... How much was it? Yeah, 140 over 99 is accurate to... Yeah, so 140 over 99 is just a little bit more accurate. This one, which is also a bit more accurate, which is 239 over 169. I wonder how they get these numbers. How do they get these numbers that are approximately, you know, like, how do you think of this? I don't know. Oh yeah, I didn't prove it's irrational to you guys. Well, I did say that, okay, radical 2, right? Radical 2 is irrational, oh yeah, because it's a prime, but why? You know? Thing is, why is radical 4 not irrational, right? I mean, this isn't enough to prove it, but I'm just trying to give you a small example as an introduction part, right, to why that one would be. So radical 4 isn't irrational because you're basically asking, like when you do a radical of a number, you're asking yourself, okay, in this case, right, what number x when squared is equal to 4? That's what you're asking yourself, right? This is very basic math. We took this in probably grade 7 and 8, so everyone should know this at this point, right? Now, if you answer this question, you get x equal to plus 2, plus 2, and x equal to minus 2, right? While the answer to what is radical 4 would just simply be 2. This is just a thing, right? Because you can't have... How can I put this? Yeah, I mean, it's just this one. You take this one, basically, just this. Now, imagine I had the same question. So, what x squared gives 2, right? Nothing comes to mind. If you don't know about radicals, and you just know about squares, for example, or powers, right? You wouldn't really know. You'd start thinking and okay, let me try, for example, 1.5. If I multiply 1.5 by 1.5, I can get something like 1.5 plus 0.75, and this would be 2.25. Close to 2, but not 2. I can try something like, for example, 1.3 times 1.3, because it's a bit more, so let's try something a bit less, right, than 1.5. 1.3, so you get 1.3 plus a third, so let's throw it on a calculator. 1.3 times 0.3, that's 0.39. Ooh, too small now. 1.69, bit too small. Let's try something like 1.45 times 1.45, right? And this would give you 1.45 times 1.45. Oh, this is close now. 2.1025, right? And you can keep just switching and shifting in between two, right? Trying to get as close as you want to 2. But you see, there is no integer, first of all, number that will get you to it. I mean, we checked, right? These even weren't integers at this point. But between 1 and 2, there are no integers, so you can't even think of integers. You have to think about fractions now, because, I mean, obviously, right? So, how do you prove that radical 2 is irrational? I should know this. Shit. I think you could just do this, if I'm not mistaken. So, saying that radical 2... you actually prove the content positive. I remember this, yeah. So, okay. Radical 2 is irrational, means it can't be written as a over b, where a and b belong to any all-real numbers, right? So, this. If I prove that I think it's like, if I prove radical 2 is equal to AB, which means if I try to show that it is irrational, and it isn't, then I can conclude this. So, let's try to prove radical 2 to be rational, okay? We'll see what happens if I try to prove radical 2. So let's say radical 2 is rational. Let's say it's rational, right? Meaning there exists a pair of integers, right? So, radical 2 is equal to a over b. Expanding, or just, natural, whatever, we square both sides. So we get 2 is equal to a over b squared, which says a squared is equal to basically 2b squared. Correct? Good. So far so good, right? And, yeah, a and b have to be two different numbers, obviously. Right. Now, knowing this, right, so a squared and 2b squared, so this says that a squared, since it's equal to 2 times something, this number is even. Why do we care? This is you right now asking. Even. So, why? Like, why do I care? First of all, a squared is even. So, a squared even. This means that a is even. This is just a thing. This is actually this is something else we could prove later on. Not right now. Actually, this is a very easy proof. If a is equal to 2k, general formula for even numbers, then a squared is equal to 4k squared, which is, you can think about it as 2 times 2k squared, and this is the general form of even number. So, yeah. Yep. So a is even. Again. So what? A is even. Does that really matter to me? We're gonna see. Apparently it does. So because a is even, there exists an integer k that fulfills a equal to 2k. So a is equal to 2k. Good. Then substituting 2k into this. Yeah. So we take this 2k and now we plug it into this. So we get 2k squared is equal to 2b squared. Right? So we get 4k squared equal to 2b squared, and then the 2 goes away here. We can divide by 2, so we get 2 here. So you get 2k squared equal to b squared. Huh, looks similar. Actually, looks really similar. This is basically this. Except now, b squared is even. Which, as we saw just a little bit up, b is even. That's it. B is even. And now, again, you're asking me, Antoine, so you proved that they're even. What does that matter at all? Like, who cares? It's even. And so, right, okay. So, if they're both even, then a over b, which is equal to 2k, over, actually I shouldn't be calling this a different thing, I guess. A is 2k, b is even, b we can write as a different number, so b we'll call it like 2n. 2n. So actually, we are able to reduce a and b further, so 2 and 2 are gone. So we get k over n now. And then we can just keep going forever, which means it's reductible. It's deductible, which means since I was able to actually reduce a over b, which is basically my entire goal of what I was trying to do here, just try to reduce a over b, that means it contradicts with one of the initial premises, because radical 2 is equal to ab, which means that this cannot be simplified. When you write it this way, this can't be simplified, right? This is the assumption. We assume this. Like, oh, yeah, this is probably true. And then when we went and proved, after proving, this is what we get. We get that a over b can be simplified, which means that this, the equality basically here, that radical 2 is equal to a over b is wrong. This is wrong, which means that actually now radical 2 isn't equal to a over b, which is basically a different way of saying, yeah, radical 2 is irrational, because you can't write it as a fraction form. Rational, if any of you don't know this, rational is the same as able to write as fraction. That's all that rationality means. This isn't. You can't write a over b for radical 2, therefore not a fraction. Anyway, that's pretty much it for today. This was a 24-minute video. I'm not gonna edit this at all probably, but hey, whatever. So yeah, I hope you guys enjoyed whatever this was. I didn't anticipate to make this video even, but I was interested in some math and some research was done. Limited at the same, but yeah, also some cool people to shout out. It's kind of messed up to say, but yeah. Apparently, Yasumasa Kanada's team in 1997 valued radical 2 to the, oh my god, 137 438,953,444 decimal places. That means like this is 10 to the power minus this decimal places of radical 2. How? Damn. Okay, I guess. Okay, sure. Sure, dude. Okay. Yeah, and then in February 2006, this was in what, 1997. This is just a little bit of history for the fans. Yeah, and then in 2006, they did it further. The record for the calculation was eclipsed by the use of a home computer. Shigeru Kondo calculated 1 trillion decimal places in 2010. Oh, okay. 2006, something happened. 2010, bro calculated one. I don't even know how much a trillion is. 10 power 12 or something. Wait, how is this? Wait, what? Wait, 1997 was more. What? Oh. Okay, apparently not. I don't know. Okay, that might not be. Okay, yeah. This might be too much. 10 to the power minus this. That is. No, this is wrong. This is stupid. I don't think any computer can do this at this point. No. I think they mean like. How can I. Yeah. Just decimal places. Don't know how what this even means because the wording is very fucked, but anyway, the most person to calculate digits for this, like the person who did the most. Damn it, move. Yeah, okay. The person who did the most is Tizian Hanselman. Yeah, he did. That's a lot of digits. 10 0 0 0 0 0 0 0 0 1 0 0 0 digits. Damn, that's a lot. He did a lot of calculations. Anyway, I'm done. I did a little bit of research and I thought it'd be kind of interesting to talk about math. I know, really don't take this video as any educational thing. It's just me learning a little bit more about math by myself and just taking you along the journey of stupid research on Wikipedia. So, yeah, hope you guys enjoyed, and I guess I'll see you in the next one, whenever that may be.